Okay, so here's our picture. E is like the Tootsie Pop, the Tootsie part of a Tootsie Pop with the Tootsie removed. It's the region between S, which is some closed surface that encloses the origin, and S sub A, which is a small sphere of radius A. Okay. So E is the region in between there, and I want to take a look at what is the boundary surface of E. Because it really comes in two parts. So it would be S plus S sub A. It's got an outer boundary and an inner boundary. And if the rule for the divergence theorem is that the boundary has to be oriented out, I know for S what that means. Out means away from the origin, because that's also away from the enclosed region. Okay. So this is going to be oriented away from the origin. Okay. For S sub A, however, out has to mean away from E, away from the enclosed solid. Well, if I'm going away from E, then I've actually got to be oriented what I usually think of as inward towards the origin. So S sub A will be oriented toward the origin. And I can say that these two surfaces together, one oriented away from the origin, one oriented towards the origin, so that both are oriented away from E, those form the boundary of E. Now, we haven't seen something like this before. We've seen piecewise smooth boundaries, but we haven't seen a surface like this that has an outer boundary and an inner boundary. Hopefully it seems reasonable that we could do this. I promise I'm going to come back and give you a more rigorous explanation, complete with a prop. We're going to use this apple to see why that works, why it's actually legal to do that. For now, I'm going to ask you to accept that that seems reasonable, if maybe a little bit questionable, and let's go with it. And then I can say, okay, I know that the triple integral along E of the divergence of F dV is equal to 0, because the divergence of an inverse square field, and remember we're working with an inverse square field for this problem, is equal to 0. But I know by the divergence theorem that that's supposed to be the flux integral over the boundary of E. So that would be the double integral over S of F dotted with N ds plus the double integral over S sub A of F dotted with N ds. Okay. The boundary comes in two pieces, so I just add those two surface integrals together. Now, if this sum is equal to 0, I can just subtract this over to the other side. So that tells me that the double integral along S of F dotted with N ds is just the opposite of the double integral along this little sphere of radius A of F dotted with N ds. Okay. That's kind of amazing, because remember, S was just an arbitrary closed surface that contained the origin. No matter what surface I choose, it's going to be the same as the opposite. The same as the opposite. It's going to be the opposite of the flux integral I get over this small sphere. Now, what's nice about this small sphere is that I can actually calculate that flux integral fairly nicely. So this is the opposite of the double integral along S sub A of, remember that F was just C over the magnitude of R cubed times R, and then we're dotting that with N ds. Well, if I'm on a sphere of radius A, the magnitude of R is A for every point on that sphere. Every point on the sphere has a position vector that points to a point on that sphere. Its distance from the origin is A. So this is just negative the integral from S sub A of C over A cubed times R dotted with N ds. Cool. That's a constant. Let's factor it out. So this is going to be negative, let's factor it out. Negative c over a cubed, the double integral along s sub a of r dotted with, now this is the unit normal vector, okay? But it's normal to a sphere, okay? Now when I have a sphere centered at the origin, r is the position vector that's pointing to that point on the sphere. I know that what's normal to the sphere, if it pointed out, would be just continuing in that same direction, and if it's pointing in, is pointing in exactly the opposite direction. So I actually know, because we're oriented inward towards the origin over this particular surface, I know that n is just negative r hat, which is r divided by its magnitude. Okay. So for a sphere, it's always very nice that the unit normal vector is just r hat or negative r hat, depending on whether we're pointing away from the center, a sphere centered at the origin, depending on whether we're pointing away from the origin or towards the origin. So that's super, super nice, because now I can say that's negative c over a cubed, double integral over s sub a. R dotted with r is just the magnitude of r squared. There's a negative sign there, so I'm getting negative magnitude of r squared over the magnitude of r ds. But again, these guys are just a's, because we're talking about a position vector that's pointing to a point on this sphere of radius a. So that becomes negative c over a cubed, double integral over s sub a. I basically got negative a squared over a ds, which is just going to introduce another negative sign and a factor of a on the top. And if it's a factor of a on the top, that's going to cancel with one of those. So I'm going to end up with c over a squared times the double integral of s sub a of 1 ds. But that's just the surface area of that sphere. Surface area of a sphere is 4 pi times the radius squared. The radius squared will cancel, and I've got 4 pi c. So I'm always going to get 4 pi c, where c, of course, is the constant that showed up in defining the inverse square field. I'm always going to get that. And what we were solving for here was the flux integral across an arbitrary surface that enclosed the origin. Really cool. For electric fields, of course, this constant is linked to the enclosed charge. And so in the study of electricity, you'll often be phrasing that in terms of what the enclosed charge would be. Okay, next video, we'll come back and we'll take a look at why it was legal to say, let's just take that outer surface oriented out and the inner surface oriented in. Seemed reasonable, but maybe perhaps a little shady, so we'll take a look at why it's actually legitimate and not at all shady.